So I had a couple questions from some students at the review sessions about mirror images and enantiomers and the nastiest stuff like that. Hard to visualize sometimes for some students when they first start out. But once you think about it, think it through a few times, picture it in your head, and once you do a couple cycles of thinking about them and successfully working out the problems, then all of a sudden it'll click. It'll be much quicker. And that's what we want to do. Some students were complaining that they couldn't use their models during the exam, but that would actually probably be counterproductive, because maybe while it would be easier for you to visualize what's going on with the actual physical models in your hand, the amount of time that you'd probably spend to build those models and build them accurately to the complexity of the molecules you're going to see on the exam, it'd be a big time sink. By the time you did a couple problems, 10 minutes would be gone, and that'd come back to bite you probably later in the exam. So what we really want to do is we want to get in the habit of being able to picture these. And like I said, some students can just do it. They're very visual, very good at imagining these molecules and how to rotate them and how to manipulate them. Other students need a little bit of work. So like we were saying, we're going to be talking about mirror images, which often is referring to enantiomers. So let's draw one real quick. We're going to have let's see, so that have our wedge coming out at us, right? That's what the wedge is. The dashed line means what? Opposite of the wedge, right? So the dashed line over here means it's going back. We'll make our dashes a little bit bigger so they're easier to see. Alright, so we can just arbitrarily move stuff on here, just making sure that we make a stereo center. So to have a stereo center, can we have two of the same substituents coming off of this center carbon? For example, can we have two methyl groups here and here? No. What about if we had two hydrogens? Could we have a hydrogen there and a hydrogen there? Would that still be a stereo center? No, right? So they all have to be unique in this case. So let's have a bromine up there, we'll have a fluorine over there, chlorine coming out here right at us, and let's have our methyl group coming, or actually I guess going back into the paper, right? So here's our stereogenic center. Now when we talk about this, I like to ask, does this have a mirror image? And I'd say 9 out of 10 students will quickly say, of course, yeah, it does have a mirror image. Everything has a mirror image. And for that other, 1 out of 10 students that have to think about it and pause, just keeping in mind that every single thing that you ever come across will pretty much have a mirror image, whether it's an atom, a television, a duck, a polar bear, a human being, anything you can think of, whether how simple or complex. If you hold up a mirror to it, and if that mirror's big enough, I guess if you had a spaceship, you need like a really big mirror per se, but let's not get ahead of ourselves there. So if you have a mirror and you hold it up to anything, any piece of matter, it's going to pretty much always give you a mirror image. So the way your book, and typically in class they talk about this, is they make this kind of a dashed line. Sometimes they make it solid. That's just arbitrary. It doesn't matter. But this mirror, well, actually, I guess the line represents the mirror, right? So this line doesn't look like a mirror, but yep, that's what it's supposed to be. So if this molecule was looking into this mirror, this line, what would it see over here? What would its reflection be, its mirror image? Well, it would actually look just like this. So our Br is still up top, right? Our CH3 and our CH3 are both going back. Our chlorines are both coming out at us, and our fluorines are both kind of pointing away from the mirror. So this fluorine's kind of pointing away from the mirror. The fluorine, the original one's pointing away from the mirror. So this, although it's a little cramped, hard to see, but if you think about it and if you look and take the time to decipher my crappy drawing, you'll see that yeah, these two are mirror images. So what happens? How do we know they aren't identical? Well, the answer to that is start rotating this molecule every which way you possibly can. So imagine the bromine down here. Let me preempt that by saying you have to keep all the connectivity the same. You can't just move the bromine down there and leave those two, right there. These have to, the whole thing has to stay static in connectivity. They aren't flowing anywhere. But when I say static, like I just said, this has to stay in this orientation compared to these other molecules, in other words. But we can take the whole molecule, put it in our hand, and toss it around like, it was a piece of chalk or a jack, etc. And we can try and orient it to, match up, so we could just lay it exactly on top and match up all these substituents. We'll find that we could do this for years and years and years, and we'd waste a lot of time and it never happened. So these two are stuck as mirror images, and no matter how we rotate them, they're never going to be superimposable. So another way, or rather another issue that a lot of students have, let's see, we'll draw another copy of it real quick. Chlorine, same molecule. So you're given one molecule, right? And then you'll be given another molecule that looks like, let's see. So fluorine, we'll say it goes backward. We'll say CH3 is forward, and our Cl is over here. So we'll have those two molecules right there. And the question will be, what are they? Are they identical? Are they stereoisomers? Are they diastereomers? So very rarely probably you're going to have diastereomers, if at all, when you just have one stereogenic center. Diastereomers are a phenomenon that's more common when you have more than one stereogenic center, just by, it's an intrinsic property of what's required to have a diastereomer actualized. So in this case, pretty much we're going to be narrowed down to enantiomers are identical. So, like we said earlier, no matter how we rotate these in any fashion, we probably aren't going to be getting them to overlap, right? So if we put that fluorine on top of that fluorine, this methyl is going to be rotating, let's see, not very far. This methyl will be on top of that chlorine, this chlorine will be on top of that methyl. So that's where the trouble comes in. It's hard to picture these in your head when you first start, and especially when we say, okay, well, are these mirror images of each other? I like to look at them and think of them as a top, a spinning top. So notice that both bromines are up, right? So if we grab this bromine and spin it like a top, so these ones spin around a little bit, can we spin it some given amount of degrees where it makes a mirror image of each other? So some students will just guess and say 50% yes or no. Other ones will actually try and think and do it and successfully do it. Other ones will just bam, in a second know the answer. So if we were to rotate it, spinning it by the BR, we'd see that if this methyl goes backwards and replaces where this fluorine is, the fluorine spins around through the back and ends up where the chlorine is, and the chlorine spins out forward and comes right out at us. Now that would match up exactly like that in the form of a mirror image. So that would kind of answer our question, that yes, these two are mirror images. So as you can see, it's kind of abstract looking at it on paper. It's a two-dimensional piece of paper, not 3D. We have to do a lot of interpretation with dashed lines going in, solid wedges coming out, so it'd be a little bit tricky. But that's what we have our excellent little models here for. So here's an example of that same stereoisomer in, what would you say, actualized form. We have a blue substituent, green, white substituent, and a red one. As you can see, those kind of could correlate with our 4 different substituents in our little drawing there. In our case, it's going to be arbitrary which one we say is bromine, which one's chlorine. It doesn't really matter. Maybe in lab that will matter for you, but in our case here, no, it won't. So if we were to make this drawing in the same orientation as our little model here, we'd actually have it like this, right? So we'd say that our methyl will be our white group right there, right? We'll say that green is the fluorine, or we'll say blue is bromine, and we'll say the red is the chlorine. So if we were to orient it like this, it would look just like this, right? The white's coming out at us, the green and the chlorine are kind of going back, and then the blue's just going straight up, right? So what about if we asked about this one's mirror image? So if I was to say visualize right now the mirror image of this molecule, could you do it? Probably, you know, for a lot of you would, and let's check your answer. So picture it, and boom. So is that what you pictured? Hopefully the answer is yes. As we can see, the white substituents match the blue, the red. Notice how both green substituents are both going in opposite directions in this case. So that, when we say visualize the mirror image of this molecule, is just like that. That's the mirror image of it. So let's talk about, maybe this is pretty clear to see, but what about if we had a molecule that was lined up like that? So we have these two molecules lined up, and the question is, are they mirror images? Or we'll start out and say, are they identical? So like we said earlier, we could sit here and rotate it. When we talk about rotating, this is essentially what we mean by rotating it. We don't mean taking the blue off and replacing it with the red. You know, we can't rip apart the molecule and do that. When we talk about rotating, we mean about rotating the whole molecule around, just like this. So we could rotate, you know, for days and days and years and try and get these to match up. We'll say we'll match up the white, we'll match up the blue, and oh, look, we don't have a match over there. We have our Christmas colors. So well, we don't want that. So let's match up our greens and see if that fixes our problem. So we matched up our greens. Uh-oh, our red and whites don't match now. Our blues match, but those don't match. So that's going to be the problem with these enantiomers. They aren't superimposable. But can we make them mirror images? So how would we do that? That's when we talk about spinning it like a top. At least that's what I call. So we have both blue groups up here pointing upwards, right? So I'm going to tell you now to spin this one like a top until it's the mirror image of that one. And we'll see if we can, you know, make that happen. So let's spinning it, see how we're rotating it, spinning it like a top, and boom. So like they are right now, we see the blues are matching, both going up, but what is going on down here? Are they mirror images yet? Well, we have a red here and a green over here, so they don't really look like mirror images yet, huh? So let's spin it a little bit more and see what happens. And alright, so right there. So what do we notice right now? We spinned it probably about, you know, maybe 180 degrees or so, and looks like we found the mirror image, huh? These two, we notice both blues are matching. Back here, both reds are matching, both whites are matching, and then our green is matching the green. They're both pointing away from each other. And that, for example, is seen again with that. So mirror image, and then in reality what the mirror image would look like. So that's kind of the gist of if you have a question talking about rotating the molecules, just keep in mind you can't detach just two of them and flip them around. That's not you know, rotating. It actually means by rotate to do this process of flipping it around. And yeah, that should cover it, I guess, for mirror images. You've seen it with an actual mirror, you've seen it on paper, and you've seen it with our model sets. So everyone should have a set at home. If you have any more problems, just, you know, bust out the set, spend, you know, all of 10 minutes doing it with yourself, and you should be able to start visualizing them in your head without having to use the models before you know it.